We often picture Hampi as a tragic landscape of ruins, a romantic graveyard of scattered stone. But the site's reality is more brutal. This is an arid climate built on solid, intractable granite bedrock. To maintain a high-density capital here, the 14th century Vijayanagara Empire had to overcome staggering environmental constraints. Their survival and regional dominance relied on solving specific problems in civil hydrology, material acoustics, and structural mechanics. At the macro scale, they manipulated gravity to move water across an unforgiving topography. At the micro scale, they altered the dimensions of raw stone to engineer precise acoustic resonance. On a metaphysical level, they overrode standard mechanical functions to construct permanent cosmic diagrams. To understand Hampi, we must look past the aesthetic carvings and decode the mathematics and mechanics beneath the stone. Hydrating a megacity in an arid zone creates an immediate civil engineering tension, moving massive volumes of water against the natural topography. This topographic map shows the primary hydrological nodes. We have the Tungabhadra River here and Kamalapura Lake several kilometers away. To bridge this gap, builders constructed a gravity-fed network of subterranean and elevated aqueducts, connecting sources through the Raya, Basavana, and Turthu canals. This network was strategically zoned. Specific channels supplied agricultural lands, while others were calibrated to feed commercial centers and royal enclosures. The physical scale of this infrastructure remains visible today. Notice the high arches and the massive granite blocks required to maintain these gradients. Once the water reached its destination, it moved into microhydrology systems, specifically the Pushkarni stepped tanks. These structures performed a dual purpose, providing advanced water retention for the population and a precise space for religious rituals. Looking at this exploded architectural view, a material anomaly isolates the Pushkarni from the rest of the city. While Hampi is built of local granite, these stepwell slabs are chloride schist, a material imported from outside the region. These imported slabs were engineered into symmetrical formations. This tightly controlled masonry ensured structural stability and watertight retention. These hydrological systems show how the empire integrated material logistics with advanced surveying to direct water through a landscape that naturally resists it. Moving from civil infrastructure to structural physics leads to the 16th century Vitala temple complex. The focus here is the Mahamandapa, or community hall, and its load-bearing stone beams. The structure relies on 56 main pillars. As seen here, each is mathematically surrounded by 7 smaller colonnettes. Carving brittle granite is notoriously difficult. Why vary the exact dimensions of these colonnettes during the structural build? This cross-section shows the answer. The architects manipulated resonant frequency. Altering the diameter of a specific colonnette changes its acoustic frequency. Furthermore, varying length and shape alters the timbre, the quality of sound. The calibrated output is standardized. Striking these pillars produces the tones of the Indian sa-re-ga-ma musical scale. This is a complex achievement given that granite is an intractable material that naturally resists fine-tuning. This calibration transforms a static architectural space into an interactive percussive instrument. In these pillars, structural load-bearing capacity and precise acoustic tuning exist within the same granite monolith, a feat that requires calculating physics alongside architectural stress. This brings us to the final artifact, the Vitala stone chariot. Standard historical assumptions frame this as a stone version of a vahana, a processional vehicle for the deity. However, applying structural analysis to the chariot's mechanical design reveals several significant engineering anomalies. Looking at this model, we see that the wheels are entirely monolithic. They lack functional spokes. This solid, static design is the opposite of the lightweight functional mechanics found in traditional wooden temple cars used in actual processions. Inside, the chariot hides disproportionately massive, deep axle housings. This extreme depth serves zero mechanical purpose for a wheeled vehicle, ruling out a simple engineering error. These housings are deep enough to anchor an immovable vertical shaft, a structural alignment with the concept of the axis mundi, the fixed center around which the universe rotates. Examining the base reveals a final piece of evidence, a network of miniature channels. These were previously dismissed as hastily carved rainwater drains. In reality, they are fluid channeling systems designed for abhisheka, ritual bathing of the structure as a static cosmic model. Each technical hurdle to mobility is actually a deliberate feature that ensures absolute permanence. The chariot functions as a yantra, an architectural diagram where mechanical mobility is sacrificed to fix a cosmological structure in time. To view Hampi solely as art is to miss the technical reality of the site. These ruins are the calculated output of a sophisticated engineering culture. This blueprint illustrates the spectrum of their capabilities, ranging from regional water vectors to microscopic acoustic vibrations. The builders coordinated material science, hydrology, and structural design into a single urban framework. They solved medieval problems using gravity and uncompromising mathematics. To understand our historical monuments, we must look past the romance of the carvings and rigorously decode the engineering mechanics holding them up.